All right, so let's take a look at 112, which is support trees. Let me get to the start of it here. And I'm not doing these live. I think just going through the steps this way is probably good enough. Um, all right, so we're going to need a data set. And in this case, we're just going to generate a random data just to have something to work on. So here's the data. We have a blob of red things here and blue things there. And the machine learning is to take the values and separate the red things from the blue things. Now, what's interesting is there are obviously many solutions. There could be a very steep line here, or there could be a very shallow line here, and they would both be 100% successful at separating the red things from the blue things. So how do you decide what the best line is? Well, the best line in the world of support vector machines is the one with the largest width to the road. Choose the line that has creates the largest difference between the two. That's how it works. So you create a model, and there you are. That's the answer. That's the line it chooses as the support vector machine. Now, one of the problems with this is it tries to make the road as wide as possible. That means you have to know the scale of these. Now, the X and the Y are scaled the same. If you were to just expand the Y scale, like measure it in different units, here we're going to multiply it by 100. Then you'll get a complete, now here it looks exactly the same, of course. It's just the axis labels that are different. This is going by hundreds and those are going by ones. But that means the same vertical difference on the scale will be counted as 100 times more error. So it's going to be very unhappy with any vertical errors and very tolerant of any horizontal errors. So it's going to choose this one now. This is a fundamental limitation of all AIs. You have to do this a lot. You have to scale data. You have to consider the units. Many of the AI parameters depend on the units being at a reasonable scale. And if they're significantly off, it will get strange results that are not really the optimum ones you're looking for. And all right, then you can have a more realistic data set, not one that's completely separate. You can expand the standard deviation. So now the data overlaps. Now you cannot perfectly separate the red from the blue, but there is an extension of the support vector machine model where you accept some overlap and some fuzziness and take some of the dots in the border to choose. And so again, now you can try. Now here, there is a C, which is a regularization parameter. C is the soft margin classification. And I forget exactly how it works, but I think it has to do with how many points. So, and what they say, with all these regularization parameters, they change the model to do something that is less perfectly selective, but more smooth. And you usually just try various values. So C went really small. Then if you move the C to 0.1, you get what looks like a pretty good solution, and so on. All right. Then you can try a curved data set. Now here, they have a C-shaped bunch of dots here and another C-shaped bunch of dots here. So the best solution would be a curvy line separating them. But support vector machines can only do a straight line in their original form. But this is a very powerful technique. Everything is pretty much a straight line. What you do is you add more dimensions. So here you have only two dimensions, x1 and x2, but then you create another measure of x1 squared and x2 squared. And now polynomials, quadratic polynomials, are now straight lines in that four-dimensional space. They're a linear combination of x squared and x. So you create these. This is kind of crazy. If you think about statistics, x squared is dependent on x. So they're not statistically independent, but that, by the way, is generally true of data sets you work with. You have multiple measures, and they are not really independent variables. So that is the way you do it. Now you add squares, and now you get a boundary like this. So you can get a good boundary there and fit it various ways. And there's something called a polynomial kernel, which is a faster way of achieving the same thing. And you can now make a 10th degree fit. And if you do, it still does pretty well. This, by the way, is what happened to Donald Trump during COVID. If I did this, like I said, I've been doing this for 50 years. The first thing I did was fit polynomials to data using old techniques. And I learned something. If you put a straight line through some data, it's easy. If you put a second or third order polynomial, it's okay. If you go to like fourth or fifth or sixth, it will make a wildly curvy, crazy thing to spike the points. This is something Excel can do by default. So in the early days of COVID, you may remember it was coming up on Easter, and about 3 weeks before Easter, Donald Trump went on and said, the number of cases right now is like 30, but it's going to fall and it's going to magically vanish by Easter. It's going to go to zero. The reason he said that is there were some COVID numbers, and somebody on the Trump team who was a financial analyst and not a medical professional put it in Excel and fit a polynomial, and it fit a high order polynomial, and it waved around and hit 0 at Easter, and they went with that instead of going with an epidemiologist model of how plagues spread. But it's an interesting issue. You go to a high degree of polynomial with a lot of parameters, you can fit almost anything, but it's going to start waving wildly all over the place. And it's going to be fitting the noise in your data and not the real trend in the underlying phenomenon. Anyway, that is support vector machines. And I think I'll stop this one and make a separate video of the next one.